Swayam Prabha. Digital India. Educated India.
Previous class I have discussed that how to incorporate the building load effect on CSR calculation and to calculate the static shear stress to determine the K alpha value. Now today I will discuss that for a clay I will check the cyclic softening. Okay. Similar way you can do it for the sand like material also to check the liquefaction. Okay. So now here these are the SU value is given and then shear strength SU or CU. So these values that you can measure. Okay. Why you can field test you can measure it. Suppose if you do the cone penetration test, from the cone penetration test data also you can measure the CU. Okay. So that means you can measure this C value at different depth, or you can calculate the undisturbed soil sample there. Based on that also you can measure the CU. Or it is better to use the field test data, so you can use that field test data, or you can collect the soil sample and the undisturbed soil sample and you can measure the CU. So that means CU or SU is known for a different depth. Okay. And here in the problem it is given the Amax by G is equal to 0.25 and MW is equal to 8, OCR value is equal to 1, so that means normally consolidated clay, and water table is at the ground level and the gamma sat is equal to 20 kilonewton per meter cube and gamma W is equal to 10 kilonewton per meter cube. Okay. So now you will check it. So first one I will consider without building load. Because there is a building whose properties are also given, and I will check for two different depths only. Similar way you can do it for other depths. So I will show you for calculation for two different depths. One is without considering building load, another is considering building load. Okay. So the building means there is a foundation load. So how that foundation details are given, that the foundation load this is your ground level. So water table itself is there and depth of foundation is 1.5 meter it is given. That's why one data is taken at 1.5 meter depth. So this is a square footing. Okay. So it is a square footing whose B value is 2.5 meter. Okay. And so that means here I can give DF, depth of foundation is 1.5 meter. Now del sigma V is equal to 100 kilonewton per meter square. 100 kilonewton per meter square at this level. So net Q net, or that at this level the Q net is itself is equal to del sigma V, and that is 100 kilonewton per meter square, and it is a square footing of B 2.5. Okay, so this is for square footing. So square footing, you know, SC is 1.2. That is the shape factor. So now first I will do it without the building load, and I will check it for your depth. First depth that I will take is 2 meter. I will check it for 2 meter, and I will check it for 8 meter. So I will check it here 8 meter and 2 meter. But you have to do it the same thing for all the depths. So 2 meter depth. So this is my CSR or tau average by sigma v dash or 0, you can say. So that is equal to 0.65 Amax by G sigma v by sigma v dash 0 into RD. So I will use this RD chart. This chart of RD I will use, and that is for m equal to 8, and 0.2 you can see it is 1, and 0.8 you can see it is around 0.95. Okay, so 0.8 it is around 0.95. RD value is for 8, it is 0.95. Okay, so that we will use for all the cases. Okay, so now for so I can write this is for your sigma v 0 is equal to, it is total, and water table is at the ground level, so it will be 2 meter, 2 into 20, it will be 40 kilonewton per meter square. Okay, it will be 40 kilonewton per meter square. Now sigma v0 dash, it will be 2 into 20 minus 10, it will be 20 kilonewton per meter square. And for 2 meter, RD value is equal to 1 from the chart. Okay, so it is 0.65, Max by G is 0.25, then this ratio is 40 by 20, and that will remain same for all the depth, because as I mentioned, I have taken a same soil layer, because if there is a layered soil whose density or unit weight changes with depth, then it will, that different layer you have to take the different density. But here the unit weight is same towards up to this 10 meter, so that's why this ratio will same, because as the water table at the ground surface. So this is your 1, so that will be equal to 0.325. Okay, now the MSF expression is 1.12 exp for MW. So I am taking the cyclic softening, so I will use this expression plus 0.828. So, and that should be greater than less than 1.13. So 1.12 exp minus 8 by 4 plus 0.828, which is equal to 0.98, less than 1.13, it is okay, because MW is 8, it is taken MW is 8. So now K alpha will be 1, because we have not taken initial without building load, so static shear stress is 0, so that means we will take K alpha is 1. So if this is the case, then we will calculate CRR for 8, m equal to 8 is equal to, what is the expression? The CRR expression was 0.8 SU by sigma V dash into K alpha into MSF. Okay, so this is the expression. So if I use that expression, so this is 0.8 into SU divided by sigma V dash then MSF into K alpha. So 0.8, this is SU at 2 meter is 50, sigma V bar is 20, then MSF is 0.98, K alpha is equal to 1, it is 1.96. So my factor of safety Fs will be CRR8 divided by CSR. So that is equal to 1.96 divided by 325. So here 6.03. So it is less than, greater than 1. So cyclic softening, that failure will not occur. So it is safe against cyclic softening. Okay. Now let's go to the depth equal to 8 meter. Okay, why I have taken this 2 depth, 2 and 8, I will later on I will explain why I have taken the 8 meter depth. So now at 8 meters, sigma V0 is equal to 20 into 8. So that is 160 kilonewton per meter square. Okay, and sigma V dash is equal to 20 minus 10 into 8, that is equal to 80 kilonewton per meter square. So your CSR or tau average divided by sigma V0 dash is equal to 0.65 into 0.25 into 160 by 80, and for 8 meter it is 0.95. I told initially it is 0.95 because your RD is equal to 0.95 for 8 meter. So it is coming out to be 0.31. Now CRR for 8, it is will be 0.8 SU sigma V dash 0 MSF into K alpha. Again K alpha is equal to 1, so it will be 7.8, and at 8 meter it is 75. SU is 75. This is SU or CU, undrained cohesion also. 75 divided by 0.31, 75 by 80. 75 by 80, MSF is 0.98 because that will not change because it is independent to the depth. So it is 0.98 and this is equal to 1. So this value will be 0.735. So the factor of safety, that is 0.735 divided by 0.31. So it is 2.37. Still it is safe. Okay, still it is safe. Now I will consider the footing load. Now consider, so this is without building load, now with building load or footing load, with I am basically taking isolated footing. It can be wrapped also, but the design procedure is same. For the wrapped, it is the same. Okay, I am doing it for isolated footing. So isolated footing, that it is given that this is 2B. So for bearing capacity calculation, that the influence zone is B, and for settlement calculation it is twice B. So influence zone will be B. So here this is my 1.5. So influence zone will be another 2.5. That is B, 2.5 meters. So influence zone will be up to 4 meter from the ground surface. Okay. So from the base of the foundation, this is 0. So up to this 2.5, your factor of safety will be same. But you have considered up to B, up to that your factor of safety is same. But beyond that, still there will be some influence of this load. But that influence of this stress or this external load, that will reduce and your depth will increase. But there will be still some presence of this stress, influence of this stress. If the influence is 0, again this will be without considering building load case, because in that case del V will be equal to 0. But until you have that influence of this load, then you have to consider that alpha, or you have to consider the K alpha factor. Now up to this factor of safety is same, that is okay, we can calculate the alpha. But beyond that, your factor of safety we have to increase, so that your effect of that stress will reduce. How will incorporate that? So I know that tau st by su is equal to what? 1 by f. That I have already shown, that tau st by su is equal to 1 by f. So tau st by su is equal to 1 by f. Now I have to calculate the factor of safety and other things. So let me just, I am doing it for depth. I am doing it for depth 2 meter. So at 2 meter, you can see at 2 meter what would be the del V, because it is 1:2 distribution of the stress. This is 1:2 distribution. Okay. So at 2 meter means, which is 0.5 meter below the base of the footing, because footing depth is 1.5 meter. So at 2 meter means it is 0.5 meter below the base of the footing. So I can calculate del V at 2 meter, that will be equal to 100 at 1.5 meter. This is square footing. So this will be 2.5 plus 0.5. So because it is 1.5 is the base of the footing, so it is another 5 meter, 0.5 meter. So del V here will be 69.4 kilonewton per meter square. So again at 2 meter, sigma V 0 for soil, that will not change, that will be 40 kilonewton per meter square. Similarly, sigma V dash, that will be also 20 kilonewton per meter square. So now when you calculate, this is for soil, only soil, but when you calculate the sigma V dash total, that is soil plus building, that will be equal to sigma V dash soil plus del V sigma del sigma V for building. So this is sigma V for soil is 20, for building it is 69.4, this will be 89.4 kilonewton per meter square. Clear? Now I will calculate the CSR considering the building load. So you know that is 1 by sigma V dash into 0.65 mx by g into sigma V soil into RD plus K del sigma V building that is the expression was given. The simplified way we can incorporate this. So that will be 1 by sigma V is 89.4, 0.65 into 0.25 sigma V for soil total is 40, RD is equal to 1 at 2 meter, that we know RD is equal to 1, sigma V 0 is 40, we can put sigma V or sigma V 0, then plus K is 0.2 and building del V at 2 meter depth, at 2 meter, because this del sigma V will change, but at 1.5 meter it is 100 kPa. So at 2 meter it is 69.4 kPa. So it will change with depth and it will reduce at depth will increase. So it is into 69.4. So it is equal to 0.23. Now I will calculate K alpha. K alpha is 1.344 minus 0.344 divided by 1 minus tau st by SU to the power 0.638. Now tau st by SU is 1 by F. So I can replace it this 1.344 and it is normally consolidated soil minus 0.344 divided by 1 minus 1 by 5, 1 by F, 0.638, and this F is for seismic factor of safety. Okay, so let me now calculate the static factor of safety for static. So that for square footing I have discussed 1.14 into SU average. I have to consider into 1.2 is the, because that is the expression I have given. Okay, 5.14 SU 1.2. So you can use it for using any expression, either Tazaki or Meharov or basic Hansen. So, but I am using that considering depth factor is 1. Okay, and safe factor is 1.2, and that is divided by Q net. So now the factor of safety Q average, SU average will be how much? So the up to the 4 meter. Influence zone is from 1.5 meter to 4 meter. So SU average will be at 1.5 meter it is 47, plus 2 meter it is 50, plus 3 meter it is 35, plus 4 meter it is 37. So I am taking the average value in between 1.5 meter to 4 meter, because up to 4 meter it is the influence zone. Okay. So that is divided by 4. So that value is 42.25 kilonewton per meter square. That is the SU average. Now that I will use here, SU average. So 5.14 into 42.25 into 1.2 divided by Q net. How much stress is acting at the base of the foundation? That is 100 kPa. So the factor of safety is coming out to be 2.61, which is safe against static load. Under static condition it is safe, because generally we take the factor of safety greater than 2.5 or 3, so it is safe. Okay. So now I will calculate the seismic factor of safety. So if I calculate the factor of safety for seismic, then it will be F static divided by 1.3. So it is 2.61 divided by 1.3, that is equal to 2. Now that means your tau ST by SU is equal to half, because 1 by F is equal to half. Now this will be up to 4 meter, Okay, after that it will change. This factor of safety value will change beyond 4 meter, because beyond 4 meter there will be still the influence of the footing load. Clear? So now if this is the case, then we can calculate the K alpha is equal to your 1.344 minus 0.344 divided by 1 minus half. Okay, you can see this is 1 by F, 1 minus 1 by half, because seismic I am taking, that is 2. So 1 by, this is half, 1 minus half, 1 by 2, that is 0.638. So if I put this, and this will be 0.81. Okay, 0.81. So MSF, that will not change whether we consider the building load or not. So for 2 meter it was 0.98, or that site itself it is 0.98. So my CRR 8, that will be 0.8, and then SU sigma V0 dash into MSF. Now K alpha is not 1, it is 0.81, because of the presence of the shear stress, and that's why this because of the presence of the shear stress your factor of safety reduces. So that you have to consider. So now here it is 0.8 into SU, as 2 meter is 50, it is 50 divided by sigma V0, which is total soil plus building, 89.4 into 0.98 into 0.81. So this is equal to 0.36. This is equal to 0.36. Okay, so the factor of safety, that will be CRR 8 divided by CSR. So this is equal to 0.36 divided by 0.23. So it is 1.56. So still it is safe if I consider that greater than 1 is anything greater than 1 is safe. But you can see that how much it is been reduced. Initially it was, the factor of safety was 6. Now it has been reduced to 1.5. If I consider that building stress, okay, that means it is important to consider that building stress when you check this cyclic softening. Okay, so this we are checking the cyclic softening. So you can do it for considering the building load if this building load is used, because there will be a K alpha, and for liquefaction it is definitely you have to consider if the soil is loose, isn't it? Because you can see then the K alpha value is less than 1. Okay, so then you have to consider for that to calculate the K alpha. So that factor of safety will reduce and it is 1.56. So whereas previous it was 6. Now I will do it 8 meter depth. Okay, at 8 meter depth, del sigma V is equal to 100 into 2.5 square. Same 1:2 distribution, it will be 2.5 plus 8 meter means your Z value from the base of the foundation is 8 meter, 1.5 meter, it will be 6.5 meter. Z is from the base of the foundation. So it is 6.5 meter whole square. So it is coming out to be 7.72. So you can see that 100 meter 100 kPa stress is come down to 7 kPa only at 8 meter, but still some effect is there. So I have to consider the factor of safety and calculate the K alpha. When there will be no sigma V dash value or negligible value, then that will be same as free field condition or without considering building load condition. Okay, so you will see that. So now here I know the sigma V 0 is for soil is already been calculated, and that is 160 kilonewton per meter square, and sigma V dash for soil is 80 kilonewton per meter square. So sigma V 0 dash for soil plus building, which is equal to 80 plus 7.72. Here it is 87.72. So as your depth increases, your sigma V dash for soil that will increase, but del sigma V will decrease. Okay. So now the CSR, that is equal to 1 by 87.72, then 0.65 into 0.25 into 160, that is for soil, into 0.95, because RD was 95 at 8 meter depth, plus K value is 0.2 into 7.72 is the del sigma V. So it is equal to 0.3. So CSR value is 0.3. Okay. Now I will calculate the factor of safety for static. How I will calculate that? Because the factor of safety, remember that if you check it for 2 meter, then the factor of safety is, I am taking is 2.61. If you check it for 3 meter, then also factor of safety will be 2.61. So up to 4 meter, then only it will be 2.61. But from 5 meter or 4 meter onwards, if it is 4.5 or 5, 6, 7, 8, 9, this factor of safety will increase. How will increase that? Because you can see up to the influence zone, F means the factor of safety is same, that is 2.61 that we have taken. up to the influence zone. So, here up to 4 meter, but here it will change. How it will change? Then the factor of safety 2.61 into Z by B. So, this way, where Z is equal to depth from the base of the foundation. Okay. So, now here Z is how much? Z is your 2.61 from the base of the foundation. It is 8 minus 1.5 divided B is 2.5. So, your factor of safety will be 6.8. So, that's way we are increasing the factor of safety so that I can incorporate the reduction of the static shear stress. I can incorporate the reduction of the static shear stress. Clear? So, so now my F static is 6.8. Now, F seismic will be 6.8 divided by 1.3. So, this will be 5.22. Now, I will calculate the K alpha, which is 1.344 minus 0.344 divided by 1 minus 1 by F. F is 5.22, 0.638. So, this value will increase, K alpha value is increase, and you will go to the value equal to 1 if the effect of that your foundation, if the effect of this foundation stress will be 0 or insignificant or negligible, when this effect will be negligible. That means you can at a depth where the effect of this external load or building load is 0, or there is no stress effect on that particular depth for this external stress due to the building load, then your K alpha will automatically come 1, because in that case your factor of safety will be so high. So, that means this part will automatically come to 1, because there is negligible effect of the external stress. So, now if I calculate the CRR, then it will be 0.8, then at that point SU is 75, then it is 87.72, then MSF is 0.98 into 0.95. So, it is 0.64. So, my factor of safety will be CRR for 8 and CSR. So, that is 0.64 divided by 0.30. So, it is 2.12. So, still it is safe, and you can see that initially it was how much? 2.37. So, now you can see the stress was only 7 kPa. So, the factor of safety is also close to that value without considering building load. But when the 2 meter depth, that there is a drastic change of the factor of safety when I consider that static shear stress or the building stress. Okay, so these are the calculations or the examples, and you can use the same technique for your liquefaction check also. The same way you can do it. So, here I am doing for the cyclic softening check, and most all the cases it is safe, it is coming out to be safe, but this is for example cyclic. So, this is for cyclic softening. So, you know, that is for clay like soil. This is for cyclic softening. So, that check we are doing. Okay. So, this way we can check, and we can check whether there will be failure of this clay like soil due to cyclic softening or not. So that means it is now it's clear how you can incorporate the building stress in your calculation, and then how you can check the cyclic softening for clay like soil, and how you can check the liquefaction for sand like soil. And the liquefaction procedure now it can be used for coarse grain soil, fine grain soil, so but provided it is Pi is less than 7. Clear? That is the criteria we have considered here. So in the next class we will discuss. So this is basically the liquefaction susceptibility criteria for coarse grain, fine grain, all I have discussed, and for cyclic calculation check the liquefaction and the cyclic softening I have already discussed. Now in the next class I will discuss how I will determine, or we will determine the settlement of a sandy soil or sandy ground under dry and saturated condition due to seismic shaking. Thank you.